now we have seen some molecular shapes, and now taking into account if we have polar bonds or not in the molecular geometry, we can determine if the molecule is polar or not, and that impacts the intermolecular forces. And you see that effect on melting point, boiling point, and solubility. So we're going to be studying that. So let's first remember that. I'm going to draw the molecules that we studied already. So that's methane, tetrahedral. We also did ammonia. And here we have a trigonal pyramidal. This is nonpolar. Here we have a permanent dipole. We're going to add up 3 vectors pointing toward the nitrogen. So net dipole. We also did water. And you start with water with 4 electron domains, but 2 are occupied by lone pairs, 2 are bonding domains, and now the molecule is bent. And we also saw carbon dioxide. This molecule is linear, and there is the 2 vectors cancel out, so 0 dipole. Molecule here is polar. You have water, 2 vectors pointing in that direction, so they add up. What is the other molecule that I drew in the previous video? Oh, okay. I had SO2, and I had BF3. BF3 is trigonal planar, and SO2, you will have a lone pair, and that impacts the geometry. Okay, so now, what are the intermolecular forces? So the molecules in the gas, they don't interact much because they are very much separated. But however, in the liquid, molecules get closer together, so they interact. And in the solid state, even more so, because in here you can have ionic bonds also in making a crystal lattice. But point here will be mostly focusing on what is the difference is the liquid phase and the gas phase, because that will impact the boiling point trend. So now, the type of intermolecular forces, the weakest that you're going to see, so from weakest to strongest, you're going to have London dispersion forces. So I'm just going to write here the word London. This is also called van der Waals. Now, second type of interaction that we're going to be seeing is dipole. Dipole. So when you have polar molecules, we're going to see that. Third, we're going to see hydrogen bonding, which is like a special case of dipole-dipole. Lastly, but I'm not going to discuss it here, you also have ion-dipole interactions. But I'm not going to be talking about ions, but yes, that's a strong interactions. So I'm going to be focusing on the first 3, which actually have a huge impact in organic molecules. So here we go. What type is this? London dispersion forces. So this has to do with non-permanent and tiny dipoles. So I'm going to say fleeting dipoles. Very small. So say that this molecule is butane. 1, 2, 3, 4. So this is a 4H10 butane, and I'm 1, 2, 3, 4 carbons. So now the nature of the bond carbon-carbon is not polar. Also the nature here carbon-carbon non-polar. And here you have 3 H's. And so let's add the hydrogens here. And you will have here at the end HHAs. And we know that these bonds are also nonpolar. We have discussed that the difference in electronegativity between these two atoms is very small, is 0.4. And we're not going to consider that polar. So here at all the other positions, you have H's. So all of these bonds are nonpolar, nonpolar, nonpolar. But what we're doing here in the line drawing is simply omitting the bonds that are carbon to hydrogen. We know we have all those. And we're also not drawing the carbon. So that's an example of a line drawing. That keeps things a lot simpler. Point is, this is nonpolar bonds. However, the bonds are made by electrons, so they do interact. So when close to another molecule, they have an effect one over the other, the movement of electrons. That's why we say this is fleeting. But to say feel that effect, they need to get close. So when the molecules are sort of linear, non-branching alkanes, they can interact better. And we're talking liquid phase. Remember that in the gas, molecules are much more dispersed. So now in the liquid, and let's add one more carbon because butane is kind of a gas. So I'm going to add a couple more. So now this is hexane. I'm going to say it's 6H14. It will be similar to this. Point is that now the chains accommodate so that there's some interaction due to these fleeting dipoles. They have very weak interactions. However, they add up in the bulk. And the longer the chain, the larger the molecule is, more carbon, the more attraction in between molecules. And here, if you have, say this is the gas, some particles very separated, and say that this is molecules in the liquid phase, to go from the liquid to, say, gas phase, I need to break those interactions between molecules. And that takes energy. So do that, again, supplying energy to break that. When the forces are weak, I don't need that much energy. So this is kinetic energy in the molecules to break those apart. And that's related to temperature. So temperature needed to do that you need to add heat, which will be transformed into kinetic energy. The molecules will separate. So the stronger the interactions, then you need more energy to break those apart. And that'll be reflected in higher boiling point. So we're talking boiling point because this is liquid to gas. Now these forces are weak, so typically, for example, propane is a gas. You use it for cooking. And the longer the alkane becomes, then the higher the boiling point. So those interactions will add up. So that is in regards to London dispersion forces present in pretty much every molecule. So in another video, I'm going to be talking of the other two that are important for us in organic chemistry, dipole and hydrogen bonding.